This is chapter number 6 of my personal book and chapter number 9 of the recommended book. We are going to have a discussion on the force and torque in this particular chapter. And the first topic of the chapter is force on a current carrying conductor. We know that when a current carrying conductor is placed in a magnetic field, the conductor experiences a force. Force is a vector quantity which has a magnitude as well as direction. So we consider figure number 6.1, and in figure number 6.1 you guys can see a current carrying conductor which is located in a magnetic field. The length of the conductor is L meter. The current in the conductor is I. This conductor will experience a force which is represented by F, and the force which is experienced by this conductor is given by equation number 6.2. So we can calculate this force with the help of equation number 6.2. The force will be equal to IL cross B. As force is a vector quantity, so for the direction of this vector quantity, we consider the cross product of these two vectors. We consider the cross product of the length vector and the magnetic flux density. And we consider the length of this conductor as a vector quantity. This vector will be in the direction of the current. Whatever may be the direction of the current in this conductor, that will be the direction of the length vector. So the cross product of these two vectors will result in a new vector quantity which will be equal to LB sine theta, and we can find out, you see, the direction of the resultant vector with the help of right hand rule, and the right hand rule will give you the direction of the force. So we can calculate the force on this current carrying conductor with the help of equation number 6.2. There is another way to calculate the force on this current carrying conductor. We consider a very small portion of this conductor which is represented by dl, and we calculate the differential force which is experienced by this small portion of the current carrying conductor. So the differential force which is experienced by the differential portion of the current carrying conductor will be equal to IDL cross B. So this is the differential force which is experienced by the small portion of the current carrying conductor. And if we want to calculate the total force which is experienced by this current carrying conductor in the given magnetic field, we need to integrate equation number 6.3. So the integration of equation number 6.3 results in equation number 6.4, and we can calculate the total force with the help of equation number 6.4 as well. So the total force will be equal to the integration of IDL cross B. Force on a moving charge. So let us discuss the force on a moving charge. We consider a current carrying conductor which is located in a uniform magnetic field, and the magnetic flux density of this uniform magnetic field is represented by B. We know that magnetic flux density is a vector quantity. This vector quantity will have a magnitude as well as direction. The length of the conductor is L. The current in the conductor is I. So there is a current in the conductor. This current carrying conductor is located in a uniform magnetic field. Definitely this current carrying conductor will experience some force. Well, we know that the current in this conductor is due to the motion of the free charge inside this particular conductor. We assume that the free charge, which is in motion in this current carrying conductor, is Q. So the total free charge which is in motion in this conductor is Q coulomb, and the current in this conductor is due to the motion of the free charge. Anyhow, we consider a very small portion of this current carrying conductor, which is represented by dl. So the force which is experienced by this current carrying conductor in a uniform magnetic field is given by equation number 6.5. This force will be equal to the integration of IDL cross B. So equation number 6.5 gives you the force which is experienced by the current carrying conductor in the given uniform magnetic field. We know that the current is the rate of motion of free charge inside this conductor. So mathematically, the current in this conductor will be equal to dq by dt. So the current in this conductor will be equal to dq by dt. And IDL will be equal to dq into dl by dt. We assume that the free charge inside the conductor travels distance dl in time dt. So if the free charge inside the conductor travels distance dl in time dt, then dl by dt represents the velocity of the free charge inside the conductor. And the velocity of the free charge inside the conductor is represented by v. So we represent dl by dt in this particular equation by the velocity of the free charge inside the conductor. So definitely IDL will be equal to dq multiplied by v. dq represents the differential charge which is in motion inside the conductor, and v represents the velocity of the free charge inside this particular conductor. So we put the value of IDL in equation number 6.5. You see, we put the value of IDL in equation number 6.5. So let us put the value of IDL in equation number 6.5. If we put the value of IDL in equation number 6.5, we obtain equation number 6.6. So the force which is experienced by this conductor will be equal to the integration of dq into v cross b, where v is the velocity of the free charge inside this conductor and b is the uniform magnetic field. We know that this current carrying conductor is located in a uniform magnetic field. We assume that the free charge moves with a uniform velocity v and in a uniform magnetic field b. So we assume that the velocity of the free charge inside the conductor is uniform, and the magnetic flux density in which this conductor is located is uniform as well. So the integration of the differential charge will be equal to the total charge inside the conductor. So equation number 6.6 can be written as the force which is experienced by the free charge inside this conductor is given by equation number 6.6. So this force will be equal to Q into V cross B. The force will be equal to Q into V cross B. It means that the force is experienced by the free charge inside the current carrying conductor. So we can conclude we can conclude that whenever there is a charge in a motion in a magnetic field, force will be experienced by the charge, and the force which is experienced by this charge is given by equation number 6.7. Now let us assume that this charge of Q coulomb moves in a magnetic field as well as electric field as shown in figure number 6. So in figure number 6 we have got a charge of Q coulomb which moves with a velocity of V in a uniform magnetic field B and in an electric field E. So there is a charge which is in motion in a magnetic field as well as electric field. So there will be two forces on the moving charge. There will be a force on the moving charge due to electric field intensity, and there will be a force on the moving charge due to magnetic flux density. As there are two sources which are creating force on the moving charge, and whenever we have more than one source, we apply the superposition theorem. So according to the superposition theorem, we will assume that the electric field intensity does not exist in the vicinity of the moving charge, and the force will be experienced by the moving charge due to the magnetic field only. So we will calculate the force which is experienced by the moving charge in the presence of the magnetic field, and then we will assume that the magnetic field does not exist in the vicinity of the moving charge, and we shall calculate the force on this moving charge due to the presence of the electric field only. And at the end we will take the vector sum of these two forces, and the vector sum of these two forces will result in the total force on the moving charge. So we assume that the electric field does not exist in the vicinity of the moving charge. So the force which is experienced by this moving charge in the presence of the magnetic field is given by equation number 6.8. So F1 will be equal to Q into V cross B. Then we assume that the magnetic field does not exist in the vicinity of the moving charge. So the force which is experienced by this moving charge in the presence of the electric field is given by equation number 6.9. This force is represented by F2. So F2 will be equal to QE. According to the superposition theorem, the total force which is experienced by this moving charge due to the presence of the electric as well as magnetic field will be equal to the vector sum of these two forces. So we add these two forces and we get equation number 6.10. So the total force which is experienced by this charge of Q coulomb in the presence of the magnetic as well as electric field can be calculated with the help of equation number 6.10, and this equation is known as Lorentz force equation. So the total force on this moving charge will be equal to Q into V cross B plus E. This equation is known as Lorentz force equation. Force between two current carrying conductors. So we consider two current carrying conductors in figure number 6.1. The current in conductor number 1 is I1. The current in conductor number 2 is I2. The differential length vector of conductor number 1 is dl1, and the differential length vector of conductor number 2 is dl2. So we know that whenever there is a current in a conductor, magnetic field is generated. So magnetic field will be generated by the current I1 in the first conductor, and magnetic field will be generated by the current in by the current in the second conductor as well. So we assume that these two current carrying conductors are located in the magnetic field of each other. We know that whenever a current carrying conductor is located in a magnetic field, the conductor experiences some force. So there will be a force on conductor number 1 due to the magnetic field of conductor number 2, and there will be a force on conductor number 2 due to the magnetic field of conductor number 1. So what we do, we consider the small portion of conductor number 1 and the small portion of conductor number 2. The small portion of conductor number 1 is represented by dl1, and the small portion of conductor number 2 is represented by dl2. So the force which is experienced by the differential portion of the first conductor due to the magnetic field of the differential portion of the second conductor is given by this particular equation. So the differential force which is experienced by the small portion of the small portion of the first conductor due to the magnetic field which is generated by the small portion of the second conductor will be equal to I1 dl1 cross db2. We know that dl1 is a vector quantity. This is the differential length vector of conductor number 1, and this vector will be in the direction of the current. So this is the differential force which is experienced by the small portion of the first conductor due to the magnetic field of the small portion of the second conductor. We know that the differential magnetic flux density which is generated by the current in the small portion of the second conductor will be equal to mu divided by 4 pi into I2 dl2 cross R1 minus R2 divided by R1 minus R2 raised to power 3. Well, keep it in your mind that R1 is the position vector of the small portion of the first conductor, and R2 is the position vector of the small portion of the second conductor. So this is how we calculate the differential magnetic flux density which is generated by the current in the small portion of the second conductor. The total force which is experienced by the first conductor due to the magnetic field of the second conductor is calculated with the help of equation number 6.11. So the force which is experienced by the first conductor due to the magnetic field of the second conductor will be equal to the integration of I1 dl1 cross B2, where B2 is the magnetic flux density which is generated by the current in the second conductor, and the magnetic flux density which is generated by the current in the second conductor is given by this particular equation. B2 will be equal to mu by 4 pi the integration of I2 dl2 cross R1 minus R2 by R1 minus R2 raised to power 3. So this is how we calculate the magnetic flux density which is generated by the current in the second conductor. Now, the differential force which is experienced by the small portion of the second conductor due to the magnetic flux density generated by the small portion of the first conductor is given by the first equation of this particular slide. So the small amount of force which is experienced by the small portion of the second conductor will be equal to I2 dl2 cross dB1. What is dB1? dB1 is the differential magnetic flux density which is generated by the current in the small portion of the first conductor, and the differential magnetic flux density is given by this particular equation. The differential magnetic flux density will be equal to mu divided by 4 pi into I1 dl1 cross R2 minus R1 divided by R2 minus R1 raised to power 3. We know that dl1 is a vector quantity. This is the differential length vector of the first conductor, and this differential length vector will be in the direction of the current I1. Similarly, dl2 is the differential length vector of the second conductor, and dl2 will be in the direction of the current I2. R1 is the position vector of the first portion of the small conductor, and R2 is the position vector of the small portion of the second conductor. The total force which is experienced by the second conductor due to the magnetic flux density of the first conductor is given by equation number 6.12. So the force on the second conductor will be equal to the integration of I2 dl2 cross B1, where B1 is the magnetic flux density which is generated by the current in conductor number 1, and B1 is given by this particular equation. B1 will be equal to, you see, B1 is given by Biot-Savart law, and B1 will be equal to mu by 4 pi. Then we have the integration of I1 dl1 cross R2 minus R1 by R2 minus R1 raised to power 3. So whenever the two current carrying conductors are located in the magnetic field of each other, there will either be a force of attraction or force of repulsion between these two conductors. So how do we come to know that there is either a force of attraction or force of repulsion between these two conductors? So let us consider figure number 6.6. There will be a force of attraction between two current carrying conductors in the figure of figure number 6.6. You see, there are two conductors, conductor number 1 and conductor number 2. These two conductors carries currents. The current in the conductor number 1 is I1. The current in the conductor number 2 is I2. These two currents are in the same direction. If you apply the right hand rule on conductor number 1 as well as conductor number 2, you see the magnetic flux in this particular region will cancel the effect of each other. The magnetic flux in this particular region will cancel the effect of each other. So the region, the space between these two conductors is known as lower magnetic field region, and the magnetic flux on this side will be greater than the magnetic flux in the space between the two conductors. Similarly, so this is a higher magnetic field region, and this is a higher magnetic field region as well. We know that the conductors will tend to move from a place of higher magnetic field regions towards a region of lower magnetic field. So definitely these two conductors will tend to move from a region of higher magnetic field to a region of lower magnetic field. So there will be a force of attraction between these two conductors. So when the currents in these two conductors are in the same direction, there is force of attraction between these two conductors. Well, if the currents in these two conductors are in the opposite direction, then there will be a force of repulsion between these two conductors. You see, if you apply the right hand rules to these two conductors, the magnetic flux in this particular region will reinforce the effect of each other. So this region will be the region of higher magnetic field. This region will be the region of lower magnetic field. This region will be a region of lower magnetic field. And we know that these two conductors will tend to move from a region of higher magnetic field towards a region of lower magnetic field. Definitely there will be a force of repulsion between these two conductors. So if the currents are in the same direction in these two conductors, there will be a force of attraction between these two conductors. And if the currents in these two conductors are in the opposite direction in these two conductors, then there will be a force of repulsion. Well, there is an apparatus which is known as current balance. We can find out the force of repulsion between two current carrying conductors with the help of an apparatus which is known as current balance. Force on a current carrying loop. You see, we consider a current carrying loop in figure number 6.8. So we consider a current carrying loop in figure number 6.8. The length of this loop is represented by L. The width of this loop is represented by W. You see, we have the unit vector AX in this direction, the unit vector AY in this direction, and the unit vector AZ is in this direction. So we assume that this current carrying loop is located in the y is equal to 0 plane. We will consider, well, the magnetic flux density is given by BAX. So this current carrying loop is located in a uniform magnetic field. There will be a force on this loop, and we are going to calculate the force on this current carrying loop. So in order to find out, you see, the total force on this current carrying loop, we will consider side AB of this conductor. We shall calculate the force on side AB. We shall consider side BC of this current carrying conductor. We shall calculate the force on side BC. Then we will consider side CD of this current carrying conductor. We shall calculate the force on side DC. And finally, we will consider side DA of this current carrying conductor, and we shall calculate the force on side DA. So we shall consider all the four sides of this current carrying loop. We shall calculate the force on each side, and finally we shall take the vector sum of all these four forces, and the vector sum of all these four forces will be the total force on this current carrying conductor. So you see, we consider side AB of this. We consider side AB of this current carrying loop. You see, the current is in the direction of the unit vector minus AZ. So the current in this side is in the direction of the unit vector minus AZ. We know that the force on a current carrying conductor is given by equation number 6.3. The force will be equal to IL cross B. We calculate the force on side AB. So the force on side AB will be equal to IL cross B. As the current is in the direction of the unit vector minus AZ, so we should consider the length vector in the direction of the unit vector minus AZ. So the length vector of this conductor is in the direction of the current, which is in the direction of the unit vector minus AZ. The magnetic flux density is in the direction of the unit vector AX. So L cross B will be equal to minus LBAY. If we put the values in equation number 6.14, the force on side AB will be equal to minus ILB So the force on side AB will be in the direction of the unit vector minus AY. We consider side BC of this current carrying loop. So let us consider side BC of this current carrying loop. The current in this particular side of the current carrying loop is in the direction of the unit vector minus AX. So we consider the force on side BC. The force on side BC will be equal to IL cross B. Now the current is in the direction of the unit vector minus AX. We should consider the length vector of this side in the direction of the unit vector minus AX. You see, the width of the conductor is W, so the length of side BC will be equal to minus W AX, and as B is in the direction of the unit vector AX. So L cross B in this particular case will result in 0. L cross B in this particular case result in 0. So there is no force on side BC of this current carrying loop. We consider side CD of this current carrying loop. So let us consider the current carrying loop in this particular figure, and then we consider the side CD, and you see that the current on this side is in the direction of the unit vector AZ. So as the current is in the direction of the unit vector AZ, we shall consider the length vector of side CD in the direction of the unit vector AZ. So the force on side CD is given by equation number 6.18. The force on this side will be equal to IL cross B, and as the current in this side of the loop is in the direction of the unit vector AZ, so the length vector will be considered in the direction of the unit vector AZ as well. So definitely L cross B will be equal to LB AY. If we put the value of L cross B in equation number 6.18, we obtain this particular equation. So the force on side CD of this current carrying loop will be equal to ILB AY. So the force on this side is in the direction of the unit vector AY. Finally, we consider side DA of this current carrying loop. So let us consider side DA of this current carrying loop, and you see the current in this side of the current carrying loop is in the direction of the unit vector AX. So definitely the length of this side should be considered as a vector quantity, and this vector quantity should be in the direction of the current, and the current is in the direction of the unit vector AX. So let us consider the force on side DA. We know that the force on side DA will be equal to IL cross B. We know that the current on side DA is in the direction of the unit vector AX. So the length vector is in the direction of the unit vector AX. The magnetic flux density is in the direction of the unit vector AX. So the cross product of these two vectors results in 0. So if the cross product of these two vectors results in 0, the force on side DA will be 0 as well. So the force on this side is 0 as well. So you see there is a force on side AB which is in the direction of the unit vector minus AY, and there is a force on side CD which is in the direction of the unit vector AY. So if this loop is free to rotate around z-axis, then this loop will rotate in the clockwise direction around z-axis. and this current carrying loop will rotate with a uniform angular velocity in the clockwise direction as the loop rotates in the clockwise direction with a uniform angular velocity. This loop will be in the state of equilibrium, and if the loop is in the state of equilibrium, the net force on the loop will be equal to 0. So let us calculate the net force on this current carrying loop. We know that the net force on the current carrying loop will be equal to the force on side AB plus the force on side BC plus the force on side CD plus the force on side DA. So if we add all these forces, we get the total force, and the total force on the current carrying loop is equal to 0. Now we are going to calculate the torque, which is a vector quantity. We want to calculate the torque on the loop. In order to calculate the torque on the loop, the total torque on the loop, we shall calculate the torque on side AB, then the torque on side BC, then the torque on side CD, and finally the torque on side DA. We shall add the vector sum of all these torques, and the vector sum of all these torques will result in the total torque on the loop. So let us consider the torque on side AB. So the torque on side AB will be equal to the moment arm of side AB cross the force on side AB. So torque is a vector quantity, and the cross product of the moment arm and the force gives you torque. So let us consider the figure. Where is the figure? Probably I forgot to bring the figure over here, so let me consider the figure somewhere else. So we consider this figure over here. You see, you guys can see a circle which is represented by AB. This circle basically represent the side AB of the current carrying loop. You guys can see a circle CD on the left hand side, and this circle CD basically represent a it represents the side CD of this current carrying conductor. So the force on side AB is in the direction of minus y-axis, and the force on side CD is in the direction of the y-axis. The moment arm of side AB is W by 2 AX, and the moment arm of side CD is minus W by 2 AX. So we consider the torque on side AB. The torque on side AB will be equal to the cross product of the moment arm and the force FAB. And as you guys have seen the diagram, in the diagram, the moment arm of side AB is W by 2 AX, and the force on side AB is minus ILB AY. If we simplify this equation, if we simplify this equation, we will get minus 1 by 2, and then we will have ILBW AZ. Anyhow, we calculate the torque on side BC, and the torque on side BC will be equal to the moment arm cross FBC. We know that the force on side BC is 0, so whatever may be the moment arm, the torque on side BC will be 0 as well. Why? Because the force on side BC is 0. Then we consider a torque on side CD. The torque on side CD will be equal to the moment arm cross the force on side CD. And the moment arm on of side CD is minus W by 2AX, and the force on side CD is IL BAY. If we simplify this particular equation, the torque on side CD is minus 1 by 2 WILB Similarly, the torque on side DA will be equal to the cross product of the moment arm and the force on this side. We don't know the moment arm, but at least we know the force on this side, which is 0. As the force on this side is 0, so the torque on this side will be 0 as well. The total torque will be equal to the sum of these 4 torques, and if you take the sum of all these 4 torques, you guys will get minus B ILW AZ. So we can use equation number 6.22 to calculate the total torque on the loop. We can calculate the total torque on the loop with the help of this particular equation as well. We have M cross B in this particular equation. What is M? M is basically equal to IS. I is the current in the loop. S is the area of the loop, and we consider this area as a vector quantity. So M will be equal to I, and the area of the loop will be equal to LW AY. So if we put the values in equation number 6.23, we have M, which is basically equal to ILW AY. We have cross B, which is equal to BAX, and we get the same equation. So we can calculate the torque with the help of equation number 23 as well.